Especially when I'm talking about energies, I find it easiest to handle that graphically. Some people really prefer to have equations. Whichever way works for you is fine, but personally I like to think graphically because it helps me keep track of my sign changes and make sure that everything works out the right way. Now, this is going to use the same set of example reactions as I showed in the Hess's law of heat summation video, where we actually did it mathematically. Now, what I've done here is I've drawn in change in energy for this part of the reaction. So what I'm saying is that I've got a bunch of molecules starting out down in this energy state. When I then apply extra heat, in other words, I have an increased enthalpy for my reaction, the products of that first reaction ended up being uphill. That's a phrase that you'll hear almost every chemist I've ever met use. So we come uphill by 180.5 kilojoules. Now, what I need to do is I need to get to the point where my only product of the reaction is 2 moles of NO2 gas. So we look at another reaction, and we see that if we reverse the reaction, we have 2 moles NO2, or NO rather, gas, and O2 gas. We combine those to form 2 moles of NO2 gas, and our table value for that is going to be negative 114.14 kilojoules. So I'm going to come downhill another 114 kilojoules in order to get to this final reactant. Now this is supposed to be the final reactant that I'm supposed to have, so this is the end of the reaction. Now what I'm going to do is I'm just going to determine how much overall change in enthalpy I had if I didn't do the roundabout way for the calculation, but instead did this straight line. So for that, we just take our 180 minus the 114, and that will give me the overall change in enthalpy for this reaction. Now, I want to remind you of a couple of things because we always have to make sure we're doing them the right way. Keep in mind that if you reverse the reaction, you've got to reverse the sign. If you change the number of moles, you have to change the enthalpy by the same multiplier. So if I had to do 2 moles and 4 moles to make 4 moles and 2 moles, it would take twice as much energy because I've actually increased the stoichiometry of the reaction, and as a result I have to double the stoichiometry of the heat. Remember that heat is going to be a reactant or a product in these reactions. Now the final thing has to be exactly the same as what your goal is. So you've got to have the same state of matter, you have to have everything in the same charge state if you're talking about things that have charges. You've got to have the same quantities. Everything's got to be the same once you do all your cross-canceling between the reactions. Make sure that you do lots of practice for these sort of problems because people do sometimes find them to be slightly tricky, but once you try out a few, they end up being pretty straightforward for you to calculate through. They can even be kind of fun